The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to this Rapid7 webinar entitled Evading Antivirus Solutions with Dynamic Payloads in Metasploit Pro. My name is Chris Kirsch, Product Marketing Manager at Rapid7. Today's webinar will take about 60 minutes. We'll record the session and send out the recording link to you in a couple of days. You can ask questions through the chat feature at any time, and we will answer the questions at the end of the session. As an attendee of this webcast, you're eligible for 1 CPE credit. You can self-report on your organization's website, for example, iscsquared.org. We strongly recommend that you keep a copy of your webcast registration email in case you get audited. And for detailed instructions, please visit bit.ly/r7cpe, and please note that the bit.ly code in the URL is all uppercase. Let me now introduce David Maloney, today's speaker. David, the light cosign Maloney, is a senior software engineer on the Rapid7 Metasploit team, where he is responsible for the development of core features for the commercial Metasploit editions. Before Rapid7, he worked as a security engineer and penetration tester at Time Warner Cable and as an application security specialist for a global insurance company. David has been a long-time community contributor to the Metasploit framework. He is also a member of the CoreLAN security team. He's one of the founders of Hackerspace Charlotte and is an avid log sport enthusiast. And now, over to you, David.
Thank you, Chris. Well, thanks everyone for joining us today. We're going to be talking about a subject near and dear to my heart that I've spent a lot of time working on, researching and developing new solutions for in Metasploit. So what we're going to talk about today is a little less on the nitty-gritty implementation details. What we're going to talk about is what are the challenges that Metasploit faces when you're talking about AV vendor products on a penetration test, and what our challenges for evading those are. We're going to talk about a little bit about what our new techniques are without going into the super low-level detail. And we're going to, more importantly, focus on how we can use these new payloads that we have in Metasploit Pro to successfully evade antivirus and IPS systems on your target systems. So let's just talk real quick, level set about some terms here. So when we're talking about antivirus, there's a couple key components we talk about. Most everybody probably has heard the term signature before. This is basically pattern matching. Like, do I see chunks of code that fit a known pattern? Do I see it do this thing, that followed by this thing, followed by this thing, resulting in this? And that's basically how signatures work. It's like regex for executable code, which this is the old way of doing antivirus. It's still used today, but is quickly becoming obsolete. And more we see things like heuristic detection. Heuristic detection is more about raising flags on suspicious behavior. So it's this idea that you simulate the execution in some fashion in an emulator or something to that effect, and you say, okay, well that looked funny, and this thing looked funny, and how many flags did I raise, and what specific flags did I raise? What can I tell about the behavior of this executable and whether that seems malicious? The big challenge for heuristic detection, of course, is how do you make concrete determinations on what suspicious or malicious activity looks like without risking false positives that could be service impacting to your customers? And a lot of AV products also come with IPS, so we're going to touch on that a little bit. Norton is going to be an example. We'll see that a lot of the versions of their endpoint protection come with a host-based intrusion prevention system, and this is basically just focused on what traffic do I see? What activity do I see as a result of this executable? What communication do I see on the wire that may be malicious? And IPSs are basically also a form of signature detection. They're just not executable. They're more traffic-oriented. So let's talk about AV detection in terms of Metasploit, because we can talk about this topic in a more generalized sense and run into all kinds of areas that don't really affect us. So there's two main areas when we're talking about dropping a payload on a system. There is when we do a direct memory corruption, where our payload is written directly into memory. This is not where we get flagged. In fact, I have never actually seen one of our payloads get flagged by antivirus in memory. Antivirus products just aren't really that good at combing through running memory to find malicious activity. There's a lot to go through there, and it becomes really difficult to tell what belongs there and what doesn't. Where we do get flagged all the time is when we have to write something to disk. This would be like, say, sending a malicious attachment as part of a phishing campaign. The PS exec module is sort of the go-to example for an exploit that requires actually writing our payload to disk and running it. There are numerous other ones, like the Microsoft SQL Server exploits, etc. And you're going to start to see these be more and more common because memory corruption is becoming less and less common in big-name software and operating systems. And with the advent of 64-bit, memory corruption is kind of on its way out. So what you're going to see more of is command injection and SQL injection and these sorts of attacks that usually rely on putting something on the file system to get an operating system level compromise. So this is where we're getting detected. So this is where we need to focus our efforts. Now, when you're talking about a Metasploit payload, in most cases, you're talking about a staged payload. What this means is that we have the payload, which is typically, the end payload is typically referred to as a stage. And we have the part that we send first that's a stager. And this comes from, again, the memory corruption world, where if you're doing a buffer overflow, you have a very small amount of space to work with. So what we created were these stagers, like reverse TCP, bind TCP. Those are our stagers. And they're a small piece of code that gets run on the system and opens a communication channel back with Metasploit to pull down the rest of the payload, the stage, and stage it into memory on that system and execute it. So the stagers are the thing that are really actually getting caught a lot of the time. So if you want to see what it looks like when we actually send a payload, it's a pretty simple process, but you can think about it this way. Metasploit sends its stager down in some fashion, whether it's an exploit or an executable that's delivered. And when we're talking about dropping an executable on a Windows machine, this is where we're typically getting caught. Yeah. So the stager goes as a file on the file system, getting caught by antivirus. Oops, wrong direction. The stager should then, if it survives, request the stage from Metasploit. Metasploit will send the stage back to the stager, which can be potentially caught by IPS because then, for example, Meterpreter on the wire looks like Meterpreter. And it's very easy for IPS signatures to pick up metserv.dll being sent over the wire. But then the stager would be responsible for loading that stage into memory and executing. And that's what the basic payload delivery process looks like when you're talking about Metasploit. So historically, there has been a lot of custom ability to generate and tweak payloads in Metasploit framework. We had MSF payload and MSF encode. So MSF payload would take all the options for generating a specific payload, and then you could pass it to MSF encode and apply various encoders to it. Encoders are actually originally designed to make shellcode that still executes, but is absent of any bad characters that are not valid for a given exploit. Now, a lot of our encoders are polymorphic, which means that they did a decent job of helping us avoid signature-based AV detection for a while. That's not actually what they were designed to do, and AV has gotten a lot smarter since those days, and what you'll find is that encoders themselves will actually bring their own AV detections with them that are similar to Packers. But as an advancement over the years, MSF Payload and MSF Encode were eventually combined into MSF Venom, a command line tool that allows you to do it all from one tool. Select your payload, set all the options, add NOP sleds, run your encoder, etc., and do it all from the command line. And you can see here in this screenshot, there's quite a lot of options available. So people have been using MSF Venom, MSF Payload, and MSF Encode to try and create AV evading payloads to varying degrees of success over the years. How does a real malicious attacker do it? Well, first of all, a real malicious attacker, you know, your APT threat, I'm doing air quotes that nobody can see, is going to probably use custom written payload. They're not going to use our payloads. They're not going to use Meterpreter, for example. Meterpreter is great, and it's great for penetration tests. It lets you do a lot of things, but we're free open source software. Everyone knows what our payload looks like. Obfuscation used to be really big, doing encoding, packing, polymorphic code generation, which is really neat stuff, where the actual payload wouldn't exist in the executable when it hits the file system, but it would write over itself and change itself into the malicious code. But those don't really work anymore. Heuristics are able to blow right through those sorts of obvious tricks. The best way is to just avoid suspicious behavior. Make your payload look as innocuous as possible. The example I like to give for this is if you're a thief trying to break into a jewelry store at night and you're waiting for the street to clear out, you could take one of two approaches. You can kind of hide in an alleyway, kind of slink back in the shadows, right? And just wait for everyone to be gone and hide out of sight. And the other option is you put on a disguise, if you will, right? You disguise yourself as a guy working on the telephone lines, or a meter reader, or somebody writing parking tickets, and you look like something that everybody expects to be there, is used to seeing, and doesn't pay any attention to. And now, in this analogy, imagine a police officer walking by. Our police officer being, of course, our AV solution. Now, in the first scenario, that cop might never see you hiding back in the shadows, and it might work. But if that cop happens to see you, and he sees a guy just standing in an alleyway hiding in dark shadows somewhere, he's going to know something's up, right? It's suspicious behavior. He's going to investigate, and he's going to probably figure out that you don't belong there. But if you're the guy working on the telephone pole, cop's not going to look twice at you. He sees guys like that all the time, every day. We're conditioned to not even notice those sorts of people. This is the same sort of approach that we are trying to bring to making our payloads evade antivirus. So why should pen testers care about AV evasion? Well, first of all, you're going to waste a lot of time butting your head against AV solutions on your target boxes. But the plain and simple thing is, why should a client of a pen tester care? Is because malicious attackers can and do evade antivirus every day. It is the lowest end of security control at this point. What AV is really good at protecting you from is those drive-by attacks on the internet. But if somebody makes a targeted attack against your environment, against your enterprise, they are going to take the time to make sure that they have a payload that will bypass your AV controls. And if you're relying on that as your main line of defense, you're sunk. So penetration testers need to simulate AV evasion because it's what the real-world scenario is. And the primary point of a pen test is to actually have a real-life assessment of what the security controls in an environment look like. So let's talk about what we're doing new in Metasploit Pro. We are now using dynamic payloads. And you might be saying, wait, Dave, I remember a year and a half ago or so, you said we had dynamic payloads in Pro, and we did. Here's the difference. The dynamic payloads we had in Pro before still followed the same old model. When we build an executable payload in Metasploit framework, for example, we build an exe that does some stuff, but has shellcode payload, the actual shellcode, in a variable somewhere that it then stages into memory and executes. Well, there's a whole bunch of things wrong with that approach. And we did dynamic exe templates before in Pro, but it still had the same fundamental problem. Our recognizable Metasploit shellcode was sitting there on the system in some form. Now, our payloads are all designed for memory corruption. That's our heritage, our lineage. It's why we made these payloads, was to exploit things like format strings and buffer overflows. But that's not how we use an executable payload. So there's a bunch of concerns when you're talking about memory corruption. We talked about size. You know, payloads that are done in shellcode have to be as small as possible so they can fit in as many buffers as possible for exploits. We don't care about size if we're building an executable and throwing it on the file system. It can be as big or as small as we want. We don't have access to the linker on our target system. So we have no idea what DLLs, what modules are loaded in memory and what functions we have access to, or even what location in memory they're in. If we're building an executable, that's not true. We have a complete access to the linker. We can dynamically link and call any API functions we want. In our framework shellcode payloads, this means that in order to call Windows API functions, we have to use a hashing routine that's referred to as block API. And after doing some digging, I was able to prove that block API itself, which is used by shellcoders all over the world, not just Metasploit, inherently is flagged by numerous antivirus vendors. If they see the block API routine, they know that this is not safe code to be running. So that brings us detections. We can do all kinds of things because we don't have size limitations. So what we've done is we said, forget this old model. We don't need to use these shellcode payloads, right? We don't need to use these shellcode stagers specifically. We can just write executables in C that do the same behavior and take the responsibility of opening that communication channel, pulling down the final payload, and staging it into memory. That's not that difficult. And then we apply some of those same old dynamic tricks that we used before, to change the executable every time we build it. So we generate random C functions. We put anti-debugging techniques in there. We randomize memory layout. So every single time you generate one of these executables, it's completely different than every other time you've ever generated one. So there's no way to signature it. But because it's also written in C and uses straight-up C APIs the same way any other executable for Windows would, it looks like any other executable on Windows would. There's no suspicious behavior. There's no weird hashing functions. There's no bizarre shellcoder trick optimizations to the code. It's actually compiled C. So it looks more and more like any other program you would run on a Windows machine. Now, aside from AV evasion, this technique also allowed us one other thing that we could not really do in our shellcode payloads, and that's error correction. Because again, space was such a huge requirement. We couldn't do error checking and retries for if the connection fails or if we run into some kind of snag. Couldn't really handle that in a shellcode payload very well. But size is not an issue here. We're just generating an EXE. We're writing C code and then compiling it. So now these dynamic stager executables, on top of all the AV evasion techniques they bring, are actually somewhat more stable from a networking perspective than a traditional framework payload would be as well. So what does that process look like now with the dynamic stagers, right? We send our dynamic stager payload. It hits the file system, blows past AV, talks back to Metasploit. Metasploit sends the stage. Now, remember when I said that this could get detected by IPS? On the framework side, and this is available to everyone, we've also turned on the ability to encode a stage in the middle of the process. So if you enable stage encoding, and this is still a somewhat experimental feature that we're continuing to work on, but when reverse TCP of our dynamic payload talks back to Metasploit in this case, before Metasploit sends metserve.dll back to the stager, it's going to run, say, Shikata-Ganai or any of our polymorphic encoders on that. So when it comes across the wire, it doesn't look like metserve.dll. And now IPS is not going to flag it either. And then that encoded stage is put into memory. It self-decodes itself and runs in memory. And now our payload is resident in memory. And once we've gotten to this point, AV isn't a concern anymore. We're already in memory, and we know we don't get flagged there. So let's talk about how we tested our new techniques a little bit. We did some benchmarking. So when I was doing an early proof of concept, all of the proof of concepts were tested on VirusTotal. And that works great for a proof of concept. It gets you a wide range of things, but there's a number of problems with VirusTotal that I won't get into. Suffice to say, for the real deal, we started setting up a representative lab environment to test in. So we tested all of our stagers against 10 prominent AV vendors in this lab. And we tested the old framework, the old Pro, and the new Pro payloads against these. In order for a payload to have been considered successful, it must complete 3 things. It must write to the file system safely and completely without getting flagged by AV. It must survive direct scanning. In other words, we put the payload on the file system. We're now going to go into that folder, select those files, right-click, scan now with, foo vendor. It has to survive that scan and not get detected. And then we have to execute it and get a shell back without AV flagging it. All 3 of these things had to be successfully achieved in order for us to score a win on a payload. And I think the results are fairly telling. So this is what Metasploit Framework's payloads look like. And you can see we did our 4 main stagers that we've done for dynamic stagers, which is bind TCP, reverse HTTP, and reverse HTTPS. The 4 stagers you are most likely to use. And we did them as both regular executables and as the service template executables that PSExec uses. And that's important because PSExec is still really one of the predominant ways to gain access to a Windows system if you've got credentials. And you can see, with the exception of a couple weird cases where, hey, it got through for some reason, but only specific payloads, and AV vendor number 7 that just didn't understand what the service executables were, we get caught on framework all over the place. It's almost a total fail. So here's what the new Metasploit Pro dynamic stagers look like. There are a couple places where we didn't get through. Strangely, on AV vendor 4 there, it was just 2 very specific stagers, the reverse HTTP and HTTPS. For some reason, it doesn't flag those as malicious. And AV vendor number 1 pretty well shuts us down across the board with a couple rare exceptions. But everyone else, we just blow right through them. And the earlier virus total results will show that this same trend basically expands across the board on all the major vendors. So we have what is not a guaranteed foolproof solution here, but what we have is tremendous results in terms of successfully evading antivirus. And because every payload that you generate will be different than the one before it, there's no way for them to do the quick, lazy thing of writing a signature for our payload and then moving on. They're going to have to rethink how they approach detecting our payloads and how they think about detecting payloads in general in order to beat this technique. So demo time. Yay, everybody's favorite part, right? Show me the money. So I've got some of our AV lab up here in a Metasploit Pro project. And now I've anonymized the vendors in these systems with the exception of the Norton 360 box because I want to show a very specific example there. So if we take, let's just take a couple of these for the sake of time. Well, I'll do a bunch of them. Hopefully my network is not running super slow today. And that, oops, no. There we go. All right. And so we can do this a couple ways. If I go to brute force, this is probably the quickest and easiest way. I will do a quick brute force, tell it I only want the SMB service, and I know what the credentials are here. And I'm going to set my, oops, I went right past it, payload options. Now, because of the network the lab is in, I'm going to have to do a bind payload. But you'll notice that I have a new option here that says use dynamic stagers for EXE payloads. This will show up in brute force. It will show up in auto exploitation. Our social engineering campaigns automatically, without any input, use the new dynamic stagers for everything. And if you select any module for a single module run that uses an executable payload, you will see an option automatically placed in there for you. So you never have to hunt for an advanced option somewhere. You never have to wonder how you turn this on. It's always right there for you automatically when it's applicable. And when it's not available, when you can't use it, it's not there. So we're going to go ahead and select that option. Actually, let me turn it off first. I'm going to launch brute force here and show you that our payloads get caught by these vendors. So with this turned off, it's going to just use the old-fashioned framework-style payloads. And this will take a moment because it's going to go through, it's going to do the brute force, it's going to do a couple other things, and then when it's done, it's going to take those credentials and run the PS exec module with those credentials against those boxes to try and get sessions. So we can see, oh, if you can see that, it starts sending the stage. Oh, we actually got on one of them. Huh, that's interesting. That box might not be running correctly right now. But what you're going to see is it's going to start sending our payloads to all of these boxes. I did uncheck that option, right? The AV should be flagging these things. Oh, don't you just love demos? Well, okay. So we got through on, oh, why is it creating sessions successfully? It shouldn't be doing that. Oh, demo. Let's see if it kills the sessions after a second here. Oh, okay. Hold on. Let's look at. So some of them, for some reason, seem to be getting through anyways. Let me just see if I can verify new connection. So, well, okay. Well, let's keep this moving, I guess, for now. None of these should be working. Okay. Is virus protection turned on? It looks like it's all on. File system shield running. Network shield running. Okay. So I'm not sure why we got through on that one. Let's see if we can actually interact with this session. Open up command shell. Yeah, okay, we can for some reason. So the natural law of demos says that that for whatever reason those systems are not behaving properly. So let's focus, I guess, on these ones that I didn't get shells on. So if I select those ones and do the same brute force again, we know that those ones got shut down before. And we're going to go ahead and do quick same options. Bind, and we're going to leave dynamic stagers enabled. And we're going to do a launch brute force again. Although I guess I could have just run psexec and saved us a little bit of time. So it's going to run through this again, except this time it's going to be slightly slower for a couple reasons. One is that it's got to compile the payloads from scratch. Another is that once the payloads run, they will actually take slightly longer than a normal payload will to run and collect the stage. And that's because, like I said, they have randomized function routines in them, so they will go through a random amount of operations before they finally get to the part where they actually request the payload and bring it back. And so what we should see is we should see a bunch more of these sessions start opening on the ones that we couldn't shell before. And we'll just start to see these all show up as shelled instead of cracked. Now, while that's continuing to go, I want to show you one specific case. And this is the Norton 360 case. And we're going to go to the Modules tab, and it'll take a little bit because I'm going over a VPN connection. But what we found when we started doing testing is, well, oh no, the payload isn't working on Norton 360, but we know that we bypassed Symantec's engine, so what's going on? So when I looked, I realized it's not AV that's actually catching our payloads. It's the IPS that was catching the stage coming back down. And that's when we decided to go ahead and roll in the experimental stage encoding functionality so that we could also successfully bypass that. I'm going to pull up the psexec module here. We'll do a bind meterpreter, and you can see here again the dynamic stager option is automatically added to that module for us. And we'll enter in our credentials with our, super secret username and password. And we're going to use dynamic stagers. And we're also going to select this option over here for enable stage encoding. And we're going to hope that the demo gods like us a little more on this one. We'll drop that back down. And so we should get our shell back here. Uploading the payload. Okay, that random error that comes up in psexec these days. Okay, and it's sending the stage. Did I not select stage encoding? I did. Oh, man, demo. Why does the demo hate me? So you can actually see, let me refresh the list here. I thought I selected stage encoding. Apparently I did not. But you can see here what I was telling you about. There's no AV detection occurring here. What it is an IPS alert, and it specifically says, Meterpreter, bind TCP. So it's seeing the behavior that it's a bind, and specifically sees that it's MetServe DLL coming down on the wire, and flagging it on that. And let's try this again. Uh-oh. 10.20.38.61. 10.20.38.61. Enable stage encoding. Fine. All right. Try this again. So you could see that the IPS is what blocked it there. The actual stager successfully got on the system, ran, talked back, and was pulling the stage down when the IPS said, oh, hey, that's Meterpreter coming down. We don't want to let that through. And, oh, man. And now the problem is that the IPS system has blocked me out of the system because I apparently don't know how to check a box properly. It should have been a clue when the task log did not say sending encoded stage, but so yep, I'm just winning at demo all over here, guys. Sorry. So like I said, those functions are built in everywhere. What you'll find is if you turn on stage encoding on the Norton 360, it'll then bypass the IPS as well, and you will successfully get a shell. These functions are enabled, like I said, in brute force and auto exploitation, and any individual module that uses an executable payload for delivery. It's also turned on by default as the standard default for all social engineering operations. But in addition to that transparent thing, we talked about generating standalone payloads for whatever reason. Maybe you're writing a proof of concept exploit and you just need something to stick in there. Maybe you're going to use social engineering in some way that we're not providing in Pro yet. You know, who knows? Maybe you've got some other vector to deliver a payload. Well, MSF Venom, if we looked back at all those options, it's really complex, and there's a lot of flags you got to remember and a lot of syntax you got to remember. And I've been working on Metasploit for 4 or 5 years, and with Metasploit for 8. And I got to tell you, I still don't always remember what all the flags in MSF Venom are. So I was sitting there and I said, you know what would be really awesome is if we just had a really nice interface for generating payloads so that people don't have to drop to the command line and remember what every flag is. It's just not super convenient. And why make people drop out of the user interface that we provide to go to command line to do something and then come back to the user interface? You should be able to do everything from the user interface that you can from the command line. So our payload generator is in the global tool setting section of the app here, and it has two sections. One is generating these new dynamic stagers. So you would just select which stager you want to generate. Let's say reverse HTTPS, because that's a favorite. And then you'll tell it which stage it's going to be. And then you're going to put in an IP address and a port, and you'll generate your payload. It'll take a second, and it's just basically writing C code and compiling it for you on the fly on the back end there. And then it'll just provide you a link to download that one-time payload. You'll click that and just download that to your local box and do with it whatever you please. You can set up a persistent listener elsewhere in the app to listen for that payload talking back, etc. So now, that's great. That's the new features. But what about all the old functionality in MSF Venom? Well, we also have the classic payload section. And this provides a much nicer interface for walking you through the process of generating any of the existing Metasploit framework payloads. So you select what platform you're selecting. Maybe it's Windows, maybe it's Linux, maybe you're trying to do a Java payload or Python or Ruby. Let's just say Windows. You can select your architecture. In this case, we'll do x86. If you're doing a staged payload, you'll select the stager, or you can turn that off to do singles. Let's do reverse TCP, interpreter. Got my octets backwards. Okay. You'll select the host, port, your exit function. Here you have the option, if you had an extra file of shellcode, you can select and upload a file from your file system containing that shellcode. And what it'll do is it'll put those two pieces of shellcode together, the payload and your added shellcode, and it will wrap them in a stub that will execute your additional shellcode in a separate thread. So it'll kick it off in a thread and then jump back to the original payload. So if for any reason you wanted to combine like an extra piece of shellcode in alongside the Metasploit payload, you could do it there. You can define a NOP sled. So maybe I want a 90-byte NOP sled in there. You can click on Advanced here and set all the advanced payload options you would want. I don't really want a NOP sled. You can, if you want, disable encoding, or you can turn on any encoder. And these options will all be pre-filtered already based on options you selected. So like if I went back here and I selected x86-64 and did a 64-bit interpreter, you'll notice that my encoder options are only 64-bit compatible payloads now. Let's put it back on x86 though. We don't want the ICAR encoder. I'm not going to talk about AV evasion, obviously. That would be funny. You can do Shikata. You can set how many iterations of the encoder you want to do. You can tell it what the max size of the payload is. So if your payload can't be above a certain size, you know, say, let's go crazy big number, but 2,000 bytes. Payload can't be bigger than 2,000 bytes. And you can't enter any bad. You can enter any bad characters that aren't allowed. So what's really nice about this is you can just start typing in bytes like this, right? Which seems like it's not that big of a thing, right? Okay, he's just typing in hex characters. But suppose you wanted to pull it right out of an exploit, right? And the bad characters are going to be defined something like this, right? As escaped byte sequences. Let's copy and paste that as if we're copying it right out of the exploit. And it just formats it automatically into this nice little hex view for you. Not a big deal, but I just think that's a really cool, nice feature. And then we have our output options. So we can generate it as an executable, and then we get all our executable formats selected here. We can do it as an EXE, a DLL, ASP page, a PowerShell script, VBS, you know, what have you. And if you select an executable, an EXE, you have the option to upload a different executable template. So, for example, if I wanted to embed my payload in calculator or calc.exe, the Windows calculator, I could upload calc.exe here. And then suppose, again, for my example, that I'm doing calculator.exe, I still want, when they click on it, for it to pop up the calculator. I can check this option for preserve the original functionality of the executable. And so what will happen is our entire payload will be executed in a thread. What happens in Framework is it'll take whatever executable you gave it, and it'll create a new text section in that executable, stick our payload in it with a stub that creates a thread with our actual payload shellcode, and runs it in a thread, and then jumps back to the original entry point the beginning of the original text section of the executable. So to the user, they click on calc.exe, they get calculator. What they don't see is that there's a separate thread running Meterpreter inside of it. Nice little functionality. We can do just raw bytes. We can just get a binary file back of the raw bytes. Or we can do shellcode buffers. So suppose you are writing this for a proof of concept. Maybe you're writing a JavaScript exploit, and we're going to do JavaScript little endian. Oops, I unselected some options here. So you can see if you don't fill everything in, it will yell at you and tell you what you haven't filled in. Okay, let's do a different. Let's say we're doing it in Ruby. What is it? I don't understand what this. Oh, I didn't tell you DLL inject. That's why you're yelling at me. All right. No. It also very much helps to pay attention to the options you pick in. I apparently need to learn how to computer harder, as I'm failing to do basic, computer operations. Where did my actual download go? Yay! Okay. Let me just see if I can pull that up to show you guys. Did I not actually download it? Oh, really? I'll tell you what, man, I seem to be cursed with the demo gremlins today. All right, turning code, let's turn that off. Shellcode buffer, Ruby, generate, give me payload. Demo gremlins. Suffice it to say, when you click on that download button, you are to get a you would get a download of the file. So in that particular case, you would actually get a Ruby file that all it's going to do for you in that case is define a buffer that you would then put inside your whatever Ruby exploit, and it would define the payload buffer for you. So you have the ability to generate from this payload generator any possible payload that is available to you in Metasploit. And you can generate it in any format that that payload is compatible in, encode it, add shellcode to it, add NOP sleds to it. You can pretty much do anything you want to a payload from within this thing and generate it and use it wherever you want. So that is pretty much it for the fail demo here. If we go back, oh no, yeah, man, I'm sorry guys, I do not know how to computer. There we go. Oh God. Okay, so now would be a great time for questions and answers as I continue to
All right.
computer.
Okay, David, and by the way, a few of the people in the audience suggested that we sacrifice somebody to the demo gods, and I've already taken care of that. Our intern is gone, and if any of the viewers would like to fill that open spot, I guess we have an open position on the Metasploit team now. So, yeah. So, a ton of questions here. Let me jump into it. So the first one, there are actually quite a few questions about UAC and bypassing UAC. You know, some people ask, hey, they use the bypass UAC module, but it gets caught by AV. What can they do? I've got another question that's related here. How do you remove UAC from the executable that you use as a template? It doesn't make sense to me, but maybe that makes sense to you. So could you talk a little bit about that?
Yes, so that's a very good point also. Right at the crunch time of this release, somebody had brought up the fact that bypass UAC also gets flagged by AV. For those who aren't familiar, bypass UAC is a local exploit. It's a privilege escalation exploit that gets you past the user access control functionality on newer versions of Windows. That annoying little prompt that always asks you, are you sure you want to do this thing that requires extra permissions? And the way bypass UAC worked is it would drop an executable. And this executable would then actually contain within itself another executable and a DLL, and would drop them in very specific places and then execute them to abuse the sysprep utility on Windows, the thing that is that runs the first time you set up Windows and asks you to like enter in your user and set up your like home network configuration, all that stuff. That sysprep runs as a trusted process, which means that it immediately bypasses all UAC prompts. And this technique abuses sysprep to make it load our DLL instead of a DLL that it's expecting from the system. And this was problematic when you're talking about AV evasion because, again, you're dropping a binary on the file system. And this was a highly publicized local exploit. And the version of the bypass UAC binary that we shipped in Metasploit framework was compiled directly from the original proof of concept source code. So right before the release, I went in and jiggered with all the source code, did a lot of cleanup, tweaked a couple things here and there, and recompiled it, and found that while, again, we don't have like 100% guaranteed AV evasion, all but a couple detections completely disappeared. And the only AV vendors that I saw that were really detecting it anymore at that point were all ones that I've never personally seen in a corporate environment. Now, I mean, that's my limited viewpoint. But the point is we went from being detected from every single AV vendor to only being detected by 3 of them. So I did that work, and the existing bypass UAC module in framework now has that functionality. So whether you're a pro customer or not, that piece will help you. But it's still a static binary, and it's probably a matter of time until they catch up to that. So we'll probably look at making the bypass UAC binaries dynamic in the same way as our stagers at some point in the near future for pro. At the same time, one of our community contributors, who goes by the name Meatballs, had also been working on bypass UAC and created a memory injection form of bypass UAC where we don't have to drop the executable that drops another executable in the DLL. Instead, we just drop the DLL onto the file system, and then he uses Railgun to hook the Windows API to inject it into memory for us, which is a very, very nice technique and is probably going to last a little longer in terms of AV evasion, but has some requirements that you have to know ahead of time on whether or not you're dealing with a 32-bit or a 64-bit system, and you have to do a little more specific configuration depending on what architecture you're dealing with. So you have both options available to you, and bypass UAC should now be much more safe for elevating your permissions once your AV evading payload has gotten you the shell, elevating those permissions to admin and completely owning that box. That answers the question okay?
If I go off mute. So I saw a ton of UAC questions. So if any of those weren't answered as part of David's response, please feel free to post them again, and I'll address them here. So next question here: by making antivirus evasion available, aren't you just enabling the bad guys?
Short answer: no. The bad guys. This is sort of like the same argument about responsible disclosure of vulnerabilities, right? Well, aren't you just arming the bad guys? The fact is, for responsible disclosure, when we find an ODE, bad guys have had it for 6 months probably, unless you're really lucky and that researcher just happened to find it while it was young. But let's take the example of Heartbleed, this new thing that everyone's kind of freaking out about, and rightfully so. It's affected versions of OpenSSL that have been around for something like 2 years. What do you think the odds really are that the bad guys, there aren't some bad guys out there that already knew about this? The same thing with AV evasion. Bad guys already get past AV. I mean, look at all these major breaches. Like, do you really think Google wasn't running any antivirus at all when they got hit by the Aurora attack? Of course they were. Did it matter? Not in the slightest. Because AV is a very limited control. I don't want to say that AV is bad or that AV doesn't work. But what AV is good for, again, are those drive-by non-targeted attacks. Any kind of specific targeted attack, the bad guys already know how to put in the work to make sure their payload doesn't get caught. The problem for Metasploit is, on the framework side, anything we put up open source, the vendors immediately grab because it's high profile and they'll signature it. This is why we have this technique in Pro, so that legitimate pen testers have a recourse that is open to them to simulate what bad guys are already doing and not waste a lot of time doing it.
Great, thank you. So one question here is, can you go back to slide 12, please? That's the entire question. And
which one was slide 12?
I don't know. There should be a number on the bottom right, I think.
Oh, yes, so there is.
Yeah, I think somebody just wants to see the slide. Okay.
Yeah, so just the requirements for these benchmarks. So if you look at these, in order for it to score the 1 point out of one possible point, these are the 3 criteria that had to be met. It had to write to the file system successfully, it had to survive a direct scan, and it had to execute and get us a shell.
Okay, great.
Those were the criteria for these benchmarking results that you see on this slide here.
Yeah, thank you. Next question here. Somebody's asking, in Metasploit Pro, can you also use dynamic payloads from the command line?
Yes. Yes, and soon to be more yes.
Okay.
So what I mean by that is, if you go to the command line and you open up the Pro console and you run the PS exec module that way, you will see that data store option that says use dynamic stagers, and you will be able to use them in any of those modules like that. You will be able to set them on the Pro modules too, on brute force, on auto exploitation. If you use the Pro console, you'll be able to do that in those modules. As for generating a standalone dynamic stager from the command line, that was a feature that did not make it out on the initial release, but should be making it out on the next update. And so there will be a Pro auxiliary module called auxiliary pro/generate_dynamic_stagers, and you will just provide it all the same options you would in the web user interface, and it will build the executable for you and just spit it out. So right now you can use it in the context of any module you would run. Standalone generation from the command line you'll be able to do on the next point release. Or not point release, the next the next update.
Yeah, okay, good. Thank you. And another question, or last question, I guess, is can you tell us about some of the challenges that you ran into with VirusTotal?
So there's 2 main problems with VirusTotal in terms of as a comparison tool. The first is one that most people, I think, are aware of, is that VirusTotal will share its results back to the vendors. So if you submit it and 10 of the 44 or 45 now, I think, vendors that are up on there flag something and the other 35 don't, VirusTotal will share those results and the file with the vendor and be like, hey, all these other guys are flagging this. You might want to look at this. So that's a problem. We used it for proof of concept because it's just a proof of concept. And second of all, if our technique can't survive that contact with the, first contact with the enemy, it's no good anyways. The other problem, and this is the much more serious problem, is that those vendors don't actually put complete versions of their, not all of them, put complete versions of their engines on VirusTotal. I know Kaspersky is one that does this, and I'm pretty sure Symantec as well, if I remember correctly. I've been told from inside sources that they don't actually put their full heuristics engines up on VirusTotal. So you will get signature detection, but you are not getting a full representative sweep of the heuristic capabilities of that product. And so we could very much get false positive results by, you know, oh, we bypass Kaspersky, and then you run it against Kaspersky in the wild, and it catches it. So we had to go to a more realistic scenario for testing.
Okay, great. All right. Thank you, David. So these are actually all the questions we're able to get today. And if you from the audience ask questions that were not answered in the webcast, please let us know. You can either reach David. I think maybe you can flip to the last slide, and I think we have your email address and Twitter handle up there. And then also, if you'd like to try out some of the features you've seen today, you can download a free Metasploit Pro trial from rapid7.com. Just go to the Metasploit section. It's posted all over there. And thank you for joining today. We hope you've enjoyed the presentation. We'll get the recording of this presentation up on rapid7.com in the resources webcast sections in a couple of days. And if you would like to get a copy of the PDF of the slides, I'd be happy to do that. My email address is christian_kirsch@rapid7.com. You also should see that in the questions pane. I think I answered one question publicly there where I have that email address in it. All right. Thank you very much, and goodbye.